do your best and give your best effort. So you give your best effort and you're like, oh, that was not good. Try again and see if you can make it a little bit better. Never hurts to try again. So everybody close your Chromebooks. Keep your periodic tables up because this is going to be periodic table related or adjacent in a way. So you want to be able to relate this back to the periodic table because essentially what we're doing here is we are counting electrons and we're counting elements. It's going to look really complicated, and let's be honest, it is going to be really complicated. Because I get used to this, if I say it's easy, just ignore me because it's not easy. It's hard. It's not math hard, so it's not like formulas and equations and lots of calculator work, but it is you writing out something that's pretty complicated. And what we're trying to do here today with this complicated stuff, which this isn't even a long one, this is just a relatively short one. We're trying to tell other people and tell ourselves how to keep track of electrons and what our electrons are doing and how many we have, where they're at, what shape cloud they're in. And the reason for this, just before I get too deep into it, we want to know what we're going to get when we mix two chemicals together. We want to know all the possibilities. And really, when you're doing chemical reactions, like we'll get to later with ionic bonding and covalent bonding, it's all about the electrons. The protons and the neutrons don't do anything. They stay inside the nucleus, and they never really move. They never really change unless you're talking about radioactive elements, which we won't get to till later. The electrons do all the business. They do all the stuff. They make all the bonds. They make all the new chemicals. And so going into the lab and just randomly mixing chemicals together to see what you get is really dangerous. That's a good way to get sick or blow something up or hurt yourself. Doing it on paper and figuring out how many electrons do I have, how's it going to bond to another atom, what am I going to make is the best way to do chemistry before you actually go into the lab and try it out. And so in order to do that, you have to know what electrons you have, what they're doing, where they're at, and how you're going to keep track of them. As I go through this, in fact, I'm going to start off right here. Y'all are going to get sleepy because this is extremely boring, and I'm going to talk for a while. So I'm going to try to keep the lights on as much as I can, unless I feel like you can't see something, and then I might turn them off for a little bit. But everybody try to stay awake, try to keep your heads up, and pay attention to this because this will not go away. You will see it on the 3 weeks test. You will see it on the 6 weeks test. You'll see it on the midterm exam and on the final exam. These are tough problems, and there's no way to like cheat your way through it. You just got to understand what it is. Now, I will say there's going to be a couple images in here that you will see on the test that once I get to the point where I can explain them a little bit better, which may not be today, they're really going to help you out with these problems. They're not too bad. I'm not going to say they're easy because they're not, but it shouldn't be something that just keeps you from getting a good grade on the test. You just take your time on it, and you will get to the point where you get it. Where do you want to sit?
Like, can I just stand up right there?
Yeah, if you want to. Yeah. That's okay. It's okay. Yeah, and today, I'm going to be honest with you, it's a boring day. I get bored by this stuff, and it's not the easiest stuff to teach. You just kind of got to drone through it. So here we go. My voice died already. That was anticlimactic. So let me give it just a second. You'll see the light come on the top left corner. It'll blink different colors, and then I'll be able to use my pen again. So any second now, we'll go to the next slide. And basically, we're trying to keep track of electrons. We're going to learn a couple new rules, and we're going to give you a couple ways to note these electrons, which is that weird stuff that I've written down over there. Those are notes on where my electrons are at and what they're doing. And so that's the name of this assignment, electron configuration. We're telling you how our electrons are configured, how they're stored, what they're doing. So starting off with the Heisenberg uncertainty principle, which we talked about before. We can't know the exact speed or the exact location of an electron. Well, we can know each of them, but we can't know them at the same time. And so this idea that we used to have atoms drawn like this, where we have a nucleus in the center and we have electrons that are kind of circling around the outside, and we say the electrons are here. This is wrong because we can't know what electrons are doing, and on top of that, we know enough to know they don't go around in circles like the planets do. They kind of move around in weird ways inside these clouds. So saying that this is how an atom looks is just wrong. So in order to do this, we had to come up with a new way that atoms look, and we made these electron orbitals, atomic orbitals. We also call them electron clouds because in a cloud, like in any random cloud, where is the raindrop? I don't know. It's in the cloud. There's lots of them in there. And it's the same thing with electrons. In any electron cloud, the electron's somewhere in there, and there's probably several electrons in there. So, just draw the general area of the cloud and say that's where the stuff is. So they have different shapes for these. And we will talk about these letters in just a second. But know the less electrons you have, the more simple the shape. So this little green dot, I'm going to turn these off so everybody can see it real quick. The green circle here, which is just a round sphere, this is S. There's only 2 electrons in there, and it's pretty simple shape. When you go up to P, you get 6 electrons, which is a little bit more complex shape. So you have 2 circles kind of smashed together, and they can be in different orientations. They can be vertical, they can be horizontal, in different angles. It's just a little bit more complex because you have more electrons and they're doing different things here. Now, you go to the D orbital, which are the brown ones here, and they get even more complex. You got donut shapes, you got 4 spheres connected together in different orientations. It's just a little bit more complex. And then I don't even know what the F orbitals look like. You can have up to 14 electrons in this one, and I guess they're too complex to really draw in a simple 3D shape like this. But just kind of remember that for the shapes. The simpler the shape, the less electrons. The more electrons we get, the more complicated the shape gets, the more little clouds you have attached to it. Does that kind of make sense? More electrons, more complicated. Less electrons, less complicated. So they're going to start off with quantum numbers. And basically what they mean by quantum numbers and your principal quantum number is energy levels. How much energy is in it? We're going to go from 1 to 7, with 1 being the least amount of energy, 7 being the most amount of energy. And if you look on your periodic table, you'll see over here to the side, we have 7 rows. Those are going to be your energy levels, your principal quantum numbers for these electrons. And so when they say that, and you have this number off to the side over here, it's a little bit more complicated, this, and there's some stupid, tricky stuff. But in general, these numbers are going to point you to what row you're at, especially when you're talking about S and P. So row 1 only has S. Row 2 has S and P. So you can see that there's more electrons and more elements each row down you go. But when they talk about principal quantum number or quantum numbers, we're talking about energy levels. We're talking about rows on the periodic table. All of this is going to be a little confusing. With each of these, I should be able to relate it back to the periodic table in rows or in groups of elements on the periodic table. So, how we write this, we're going to start writing them now, because that's basically the whole point of all this, is that you're able to write these down in sequence. We have we have a number, and then we have a letter next to it. The number is going to tell you the row, like I said, or the energy level, and I have that written down over here. Energy level is going to be your number. The letter is going to be your block in the periodic table, and I'm actually going to skip forward a couple slides and show you this so everybody kind of gets it from the beginning. We have 4 different levels, S, P, D, and F, and they kind of talk about them here. S, P, D, and F. These don't mean anything to you yet. When I show you the periodic table, it'll make a little bit more sense. Maybe I should move this slide further to the front. Come on. Here is actually how the periodic table is divided up by your orbital levels. I'm going to turn this back. Well, I'll leave it off for a second. The S block are these first 2 columns. So you can see on your periodic table, everybody look at your periodic table. The orange and the yellow rows are your S block, including hydrogen and helium. Notice how helium's kind of all over here by itself, and hydrogen has a spot right next to it where helium could go. Technically, when you're talking about electrons, helium does move over there. The reason we put helium all the way over to the right is because it's also a noble gas, and so it makes a little bit of sense in both places. For electrons, imagine helium right over here next to hydrogen in these two columns. These are going to be your S block columns. So it says it right here, S block. And you will actually get an image almost exactly like this for your test. You'll have a periodic table that says S block, D block, P block, and F block. So if you move helium over, then you should be able to see you have a nice rectangle right here on the right side. Not including the pink elements, you have the light blue, the dark green, the light green, and those two different color blues. That's like a nice rectangle right here. That is your P block. So you have S on the left, P on the right. Now in the middle, you have the pink elements, which are all your transition metals. Those are going to be the D block. And at the very bottom, the two little rows of elements we'd hardly ever talk about and rarely use are your F block. The F block is the biggest. So we have those 4 different sections of the periodic table, and I want you to kind of think about that, how we section that off. These 6 rows, or columns, these 6 columns, these 10 columns in the middle, which are all pink, and then these 2 rows down here at the bottom, which are your F block down here at the bottom. So we have S, D, P, and F. And as we go through this, we'll use these quite a bit more, and you should get a little bit more familiar with them. But let me go back to the beginning. Here we go. So when we say 1, we're talking about the top row. When we say S, we mean these first 2 elements in that S block, which are only really hydrogen and helium. Is there anything else in the first row? No. So 1 will never have anything other than S. There won't be any Ds. There won't be any Ps or any Fs. 1 only has S. And that kind of matches up with what you have in the periodic table. The first row only has those 2 elements. They both belong on the right side over here, which is S. As you go further down, you get more little blocks that are available to you, and so it can get more and more complex. So higher principal energy levels contain more sublevels. So the more energy you get, like all the way down here at row 7, you have all sorts of other sublevels. On row 7, you have the S, you have the D, you have the P, and you have the F. So they contain all 4 of them. As you go up, you get to row 5. Row 5 doesn't have the F sublevels. It only has S, D, and P. As you get up to row 3, there's no D in row 3. It's just S and P. And then as you go up, you even get rid of the P. Top row, the first row only has S. Does that kind of make sense? So 1 starts off with S. 2 and 3 have S and P. 4 and 5 have F, S, P, and D. And then 5 and 6 have S, P, D, and F. It just gets more complicated the further you go down and the more electrons you get. They're going to mention sublevels. I'm not going to talk about sublevels a lot. Sapling's going to talk about sublevels a little bit. The best thing you need to know is when you're counting electrons, 2 electrons fit into each sublevel. So if you know the S block has 2 electrons, which is really the most important, you don't need to remember the sublevel stuff. Just remember that you need to divide by 2. So 2 divided by 2 gives me 1 sublevel. For the P block, you have 6 electrons because it's 6 elements wide. Boron, carbon, nitrogen, oxygen, fluorine, neon. 6 elements across. There are 6 electrons. If they ask you about sublevels, divide that by 2. You have 3 sublevels. I'm not going to spend a lot of time talking about sublevels because, to be honest, we do this stuff a lot more often than we do the boxes and the arrows on sublevels. There'll be a couple questions on sapling, but I don't think it's a lot. So, again, when you look at this, just know that you have double the amount of electrons for sublevels. S has 1 sublevel, but 2 electrons. P has 3 sublevels, but 6 electrons. So you just double. There's 2 electrons in each little box here. Okay, so what is an electron configuration? That's kind of the whole point of what we're doing. It's a set of numbers and letters that describes an atom's electron arrangement. And this is important because we need to know what the electrons are, where they're at, how many we have, and what they're doing, what kind of orbital they're in. We're going to start with the basic one. This is called the ground state electron configuration. It's just the normal one. Unless they ask for the noble gas configuration, the ground state one is the normal one that they're always going to ask for. And they may not even call it ground state. They might just ask for the electron configuration. So the ground state is going to be the full one, the more difficult one that is that you have to do. It is also the most stable one, so more than likely you're going to have neutral atoms that are kind of stable. We have three principles that we're going to go over. They have the Aufbau principle, the Pauli exclusion principle, and then the Hund's rule, which we'll kind of cover in just a second. Basically, these just kind of help you understand how the electrons do what they're doing. So the electrons retrieve the ground state by occupying the orbital closest to the nucleus, since it has the lowest possible energy. And think of it this way. The electrons are what charge? They're negative. What charge are the protons in the nucleus? Positive. And what do negatives and positives do? They attract. They're going to come towards each other. So when you have the protons in the nucleus, the electrons are always going to want to be as close as they can be. They're going to fill in those desks. In the same way, if I told you you were all negative and the board was positive, when you come into the room, you're going to fill up the first row first before anybody sits at the second row. And every student that comes in the room will just get the closest seat they can to the board before they start to fill up the back rows. Obviously, that's not how it happens in real life. But if you were electrons, that's what you would do. So that's what the Aufbau principle says. The principle states that the electrons fill the available orbits with the least energy first. And so they're putting off the least amount of energy by getting as close as they can to the protons in the nucleus, allowing that attraction to happen. So the Aufbau diagram shows this, which you will see. I may put this on the test. I may not. This highlights one of the first problems. Things start off going in order, and then they get out of order kind of quickly. And what messes it up is the D block and the F block. So your pink elements in the middle and your two rows at the bottom. I don't have a great explanation for this, but the numbers are off. Like, what row does your pink block start off in?
4.
It starts off in the 4th row, but you'll notice here that first row in the D block, the top row, is not 4D, it's 3D. So as far as the electrons are concerned, that whole block is like shifted down one. And so that becomes a problem because you got to remember that this first block is 3D and not 4D. The bottom two rows are the same. What rows do the green and gold fit into? 6 and 7. They're not 6 and 7 though. They're 4 and 5, which also doesn't make a lot of sense, but that's just how the electrons do things. And so as you go up, you kind of go in order. You start at the first row with 1s down here. Then there is no P or D for the first row, so you go to the second row. 2s. They have that right here. You come over like you're reading a book from left to right, top to bottom. You come over and you get to the first row in the P block, which is 2P. So they have that. Then you go to the next row. 3s right here. 3P right here, the second row of the P block. And then we have a problem. There is a 3D, but it doesn't come until after you get to 4s, which is kind of why it's all shifted down. So they're going to fill the 4s first, then they're going to fill the 3D area. So it still goes in order as you're reading left to right. Just remember that not everything in the 4th row starts with the letter 4. And you can see that over here. 1s, 2s, 2p, 3s, 3p. I start on the 4th row, but when I get to the D block, it's not 4D, it's 3D. Yes.
Do you think the reason why that is because technically this should be here? So the reason why it's 3D not 4D is because this is not here and then move down?
No, it's more to do like on the physics level with what the electrons are doing and why they're filling those spots. Because that would kind of make a little sense, but when you look at the F rows, they're not 6 and 7, they're 4 and 5. And so it basically, those spots in the electron configuration are actually on the 4th energy level. So they fit along with everything else that's 4, 4s, 4p, 4d, 4f. They just don't get filled until the 5 and 6s have kind of already started. And so this is a little bit more complicated than high school chemistry. If you were taking a college chemistry class, they might get more in depth into why those are offset. To be honest, I don't even know if I know fully how to explain it. But it has to do with the energy level of the electrons and the order that they get filled, and they're not always in the proper order because of the way they sit closest to the nucleus. So the good news is you don't really have to know why, and you don't even really have to be able to read this. We will have a much better image that kind of shows you how to go through this process step by step. The main thing that I want you to remember when we get to this is that you're always going to go in this order: S, P, D, and F. So from left to right, you go S, P, D, and F. Well, I guess that didn't. It's not always S, P, D, and F. For that energy level, it's S, P, D, and F. But sometimes it gets out of order because you notice from left to right on the periodic table, the way you write this out, after 4S, you get to 3D. So you're still going to go left to right on the periodic table, but that's why the numbers are off there. We will have a better image that I'll show you in just a second. I'm going to turn the lights back on. That will help you out with this. So the main thing I want you to remember is when we're doing this, it's all about what block you're in, S, P, D, and F, and how many elements are in that block from left to right. So how many columns are in the S block? 2. So there can only be 2 electrons in each of the S block orbitals. And if you look up here at all the S's, 1s, 2s, 3s, and 4s, what's the exponent? 2. On all of them, it's 2. That's as high as it can go. There can only be 2 electrons in there because there's only 2 elements wide in that column. So when you go to P, how many elements wide is that block there? 6. So for all the P's, unless you get to the very end and you're stopping, which I'll get to stopping in a second, all of your P's are going to have 6 elements or 6 electrons in them because that's how many elements wide it is. So essentially what we're doing here is we are counting atom to atom like you're reading a book and you're adding up your electrons. So 1s has 2 electrons, 1 for hydrogen, 1 for helium. 2s, if you go to the next row, has 2 electrons, 1 for lithium, 1 for beryllium. Then I go to 2p, and it has 6 electrons, 1 for boron, carbon, nitrogen, oxygen, fluorine, and neon. So I'm literally just counting them. 3s, we go back to the next row, sodium and magnesium, 2 electrons. 3p, we come back over here to the p block, 6 electrons for aluminum, silicon, phosphorus, sodium, chlorine, argon. You're literally counting electrons, and at each little block, you're telling me what energy level it's in and what shape the orbital is in, where the electrons are at, what they're doing, essentially. Until you get to the end, and we'll get to that in just a second. I don't want to get too far out ahead. But you're literally counting. So how many elements across is the pink block? 10. You have 2 for P, 6 for S, and 10 for D. And now we have one problem because our periodic table is a little bit wonky. How many are on the bottom here across the green and the gold?
16.
It's actually 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. So it has 15. Note that the last 2, LU and LR, they actually have in the pink block, they've kind of taken that space out and made it green and gold up here in the pink block. The bottom rows actually have 14, which makes more sense because if you're dividing by 2, you'd end up with 7. So the bottom row for F is 14. You're not going to use that too much, but do try to remember it. So 2, 6, 10, and 14. 2, 6, 10, and 14. That's kind of the most important part that's going to help you get through these problems pretty quickly. So, yeah, we've already done this. I didn't know if I need to go back or not. Now, the highest energy electrons of a neutron or a neutral atom will be found in the sublevels indicated by period and the block of the period containing the element. This is actually what you're going to get on the test. It has everything lined up properly, and it shows you the order that it comes in. So you can start here. It says begin here, and you're going to go left to right until you get to your atom. And they even have it kind of drawn out here as long as you can remember the number of elements that you have in each area. So we have 1s with 2 elements, 1s squared here. 2s with 2 elements, then 2p with 6 elements. 3s with 2 elements, 3p with 6 elements. And you just keep going down the rows, and it's going to take you all the way until you get to the last row that has S, F, and D. Note that it also has the proper numbers written in here. So you don't have to remember that 3D is in the 4th row, right in between 4S and 4P. It just tells you that. It's 3D here. And so as long as you can go through here, count your little boxes for each element, you should be able to go the entire route, however far they need you to go, and stop it where you need to stop. Now, we get to the most important part. This is not the most important part. Pauli exclusion principle basically states that each orbital can hold a maximum of 2 electrons. So they talked about orbitals earlier. Just remember, if they ask you about orbitals, find out how many electrons you have, divide by 2. So in the S level, we only have 2 electrons. So how many orbitals is there? Just 1, and it holds both the electrons. Now, how do you fit electrons together so closely? We discovered that electrons are actually spinning, almost like you would spin a basketball, but instead of left and right, we call it up and down. So you have up spin and down spin. If electrons are spinning the same way, apparently they won't be close to each other. If they're spinning the opposite directions like they have right here, they will sit close to each other. And I think the next thing they're going to mention is basically Hund's rule, which is just like you would as students filling in these rows as you file into the class. Let's be honest, you're not going to sit next to somebody unless you have to. If there's an open seat, you're going to take the open seat with nobody right next to you so you can have plenty of elbow room. If you have to fill in that seat, you will. Another example is the middle seat on a plane. If you've ever flown Southwest, they let you sit where you want to. The middle seats are always the last to fill up because no one wants to sit in the middle seat. You either want the window or you want the aisle. That's it. The last people on the plane always have to get the middle seat. The same thing works with electrons. If there's an empty seat over here, these 2 electrons aren't going to sit next to each other. They don't have to, so they won't. They will spread out as far as they can until there's no empty seats left. Then they will kind of fill in the middle parts. And so if they ask you about that, know that they got to spread out first, and then they will start to fill in your empty spots. Okay, the boxes and the lines, we don't really do a whole bunch with that. If they ask you a question on that, on sapling, just let me know, and I'll come help you out. What's important here is how we actually start to write stuff and what this means. So they're going to start off by giving you an electron configuration, and they're going to ask you, what element does this work for? Later, after you get a little bit more used to it, they will give you the element and ask you to write out the electron configuration. But here's what we're looking for. And I'm going to turn the light on real quick. This goes from 1s all the way to 3d. But notice it doesn't have 3d10 for all the electrons in that row. It stops at 3d5. So we want to know what electron that means, what atom they're asking for here. So we're going to go down the list. 1s squared with 2 electrons, hydrogen and helium. 2s squared, lithium, beryllium. 2p to the 6th power gets us through neon to the end of that first p row. 3s squared is sodium and magnesium. 3p to the 6th power is aluminum through argon. 4s squared is going to be potassium and calcium. Now we get to 3d. So note again, 3d is in that 4th row in between 4s and 4p. but we don't get all the way to the 10th element in 3D. So that's actually where we're going to stop. How many elements over do we get?
Or no.
5. So count over from the beginning of the pink, count over 5 elements and tell me where you stop.
Iron.
Nope, you went one too far. So start as 1 with scandium. Manganese. It's a weird one. It's like, it sounds like magnesium. Your brain wants to say magnesium, but it's manganese. So the 5th element in that pink block there on the first row, which is 3D, that is manganese. That's the element that we're talking about here. And look at something that you can do. This is a trick that will help you do it a little bit easier. Add up all of your exponents and see how many you have, because each of these exponents is the number of electrons that's in that row. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus another 2 is 20. 20 plus 5 is what?
25.
25. How many protons does manganese have? 25. So if I have 25 protons and 25 electrons, I have a neutral atom, and I should be good to go. So that's what they're doing here. And you'll notice as we start to write these out, they're all going to be the same. They're all going to start out the same way. 1s, 2s, 2p, 3s, 3p, 4s. The only thing that's usually different, and you do have to keep an eye out, is that last one. That's going to tell you where to stop and how far you're going to go and help you get to your answer. So let's see. Do they have anything else to say? Oh, the noble gas configuration. This one is a little bit long. It's not too bad. This is actually one of the shorter ones. But you can quickly see you don't want to have to write all this stuff all the time. If they ask you to, you're just going to have to do it. Some of them will get really, really long. I will point out that manganese is not very far down on the periodic table. So they can get a lot longer than this. But they recognize that this is kind of a waste of time to have to write all this out. So what if we just start at the row that our element is on? So if I find manganese, what row is it on? The 4th row. So I just start at the 4th row, and I start at the very beginning, 4s squared, and then I count over till manganese, till I get to manganese, which is in the 3D row, and it's my 5th element over. So that's just the very end, the last row that I did, but I have to give them a starting point, because I can't just start off here. That's not acceptable, apparently. So we call this the noble gas configuration. Where are the noble gases? Look in your key here. Find the noble gases. Where are they at on the periodic table? Yeah, they're in that last column, all the way to the right. These are your noble gases. And they call them noble gases because they're not really reactive. They have all the electrons they could possibly want. They don't need anybody's stuff. They don't bond with anything. They just hang out by themselves all the time. So you want to give the last noble gas that you crossed as you were going through here. So you didn't get all the way over in the 4th row to krypton. So what was the last one that you wrote about? It would have been the one above that row in row 3, argon. And so that's what we say here. We put argon in the square brackets. It has to be the square brackets. Then you can start writing out the rest of your electron configuration. And note that if I just stopped right here at 3p6, all of this would essentially tell me what argon is. And so I'm kind of taking this and abbreviating it down to just say that's argon, and then I'm going to start here and finish all the way until I get to manganese. So I believe, yes, that will probably be the end. I will leave this chart up to help you out a little bit, and I do have one thing to kind of show you on the periodic table. Actually, maybe for tomorrow, I will print this one page out and give it to y'all so you can kind of use it a little bit. But where are we at? Here is a problem that they give you on sapling. Usually they don't do this too bad because it's kind of hard, but I will point out they mess with you right here. They don't give you both elements in 4s. If you look over here, we have manganese. It's 4s2, 4s squared. If you come back over here, do they have both electrons in the 4s? They don't. So I have one less electron, which means it's not going to be manganese. And so count up the number of electrons you have here with your arrows and see what element it is. They're going to ask you what is the element. And they're going to ask you to write out your electron configuration. It's going to be the same thing as we wrote out for manganese, but when you get to 4s right here, instead of writing 4s2, there's only one electron, so you need to write 4s1. But there are still 5 electrons in the 3D area, so you have 5 electrons there. So I know this is kind of difficult. While you're working on it, pull up the study sheet that I put on Google Classroom. That will help you with the first question, which is like the different orbitals. And if you have any questions, let me know. You should have questions. Please ask lots of questions because this is not a simple thing. So hopefully this lecture was a little bit better than the first one I recorded. And it's about the same time. So we'll see. Maybe I'll just post both of them. I don't know. Have a nice day. And if you have questions, email me. And I don't know if I should say this, but if it's getting very difficult, consider coming back to class because it's probably going to be really hard for you to learn this stuff at home. Just watching YouTube videos. But I don't know. Maybe it'll be easier. If you're doing good at it, then continue doing what you're doing. But we're all here. Say hi, class. Everybody says hi. Yeah. Nice. So have a nice day, and I'll talk to you tomorrow.